Hello everyone, I'm Michał Trojanowski from Curity. Welcome to part 1 of the course Building an Identity Architecture. This part is an introduction to the neo-security concept. We'll focus on introducing you to the concept of neo-security and then taking a closer look at the three main parts of a system which adheres to it. These are the Identity Management System, the API Management System, and the Entitlement Management System. The neo-security architecture is a centralized and modular security architecture based on open standards. It is designed to secure, protect, and assert legitimate access to APIs, services, and applications on the web and mobile. It manages identities, governs the issuance of tokens, and is responsible for federation, critical for building a secure and scalable platform. Computer programs are built by breaking down complex problems into smaller and smaller pieces. The problem is broken down until each individual piece can be comfortably reasoned about. Then, they are assembled into a working whole that solves the difficult problem. And creating a neo-security platform is not much different. The whole problem of a robust security is broken down into smaller and smaller pieces, which can do their job well and integrate with other components. The definition of neo-security can be broken down into two principles: separation of concern and standards-based. Separation of concern comes from the Unix philosophy. As Doug McIlroy said, write programs that do one thing and do it well. Write programs to work together. You want each part of your security architecture to be focused on just one concrete problem. Thanks to that, you can have a greater level of certainty that a component does its job well and has no security flaws. The services making up the larger component must, of course, exchange information. They can do it using proprietary APIs, but it's best if they conform to standards. Using standards helps you mitigate many known issues and gives you more freedom of choice. If your components connect with others in a standardized way, you can easily exchange them for new ones, thus preventing vendor locking. Once you start connecting your system using homemade protocols, it will be very hard for you to exchange parts of the system. And what is more, choosing technologies which conform to standards or implementing such means that it will be much easier for your organization to abide by any laws it may be required to, like the PSD2 in financial-grade APIs, or in the privacy field, GDPR, or the American counterpart, CCPA. So let's reiterate. Neo-security architecture is about having a modular platform based on open standards. And when we think about the modules that a security platform needs, we can extract three groups: the Identity Management System, the API Management System, and the Entitlement Management System. Let's have a closer look at each one of them. What are their roles and what services they consist of? In order to have a secure identity management system, you need at least these components: an identity store, a profile service, an authentication service, and a token service, each one having its own distinct role. The identity store's responsibility is to securely store your user's data. This will be data needed to perform both authentication and authorization. While properties like usernames, emails, or passwords are usually used for authentication, you may also need to keep any other information that will enable the system to perform authorization decisions. For example, user's role, their status, or age. An identity store can be a local database or an external source, like an Active Directory or some proprietary REST service. Whichever the type of the identity store, remember that its sole responsibility is to securely keep the user's data and provide an interface to create, read, update, and delete it. The profile service should be your frontend to the identity store, a service which enables you to manage and update identities. The profile service should be the only one which directly contacts the identity store in order to abstract the protocol used by the identity store. The identity store could be an SQL database, a NoSQL database, an Active Directory, or a REST service, and it should not be a concern to any of your other services how to read users' data from the store or how to write them. The profile service serves pretty much the same role as a repository does in a modern programming framework. The profile service exposes an API the other services can consume, without needing any knowledge about the underlying identity store. A popular standard used by profile services is the SCIM protocol, System for Cross-Domain Identity Management. It is a specification of an API exposed by a profile service. An authentication service's role is a very important one. It is supposed to authenticate the user. In other words, to make sure who is the user that initiated the request. The authentication service must perform a set of actions that will eventually enable to connect an entry from the identity store to the request. As a result of successful authentication, the authentication service issues a set of assertions of claims about the user. It is a set of data about the user that other services can trust. Once the authentication service says that user X sent the request, all of the other services will trust that it is in fact user X. And that puts a lot of responsibility on the authentication service to do its job right. Although there are standards for concrete authenticators like the Universal Second Factor, UTF, the time-based one-time password, TOTP, or WebAuthn, the authentication as a whole process is not standardized. So it is the authentication service's role to incorporate all the standardized and non-standardized authenticators into one complete flow. Even though the authentication service has only one responsibility, to authenticate a user, it is a difficult task. And it can get even more difficult if you take into consideration that a modern authentication is a complex flow. It's no longer just a user providing their password, but a complex path with many different authentication methods and actions that can be undertaken. Things like multi-factor authentication, time-based filtering, or geolocation filtering, just an example. You can imagine the authentication service denying authentication if the user tries to log in from a location they should not be in, or to require a second, stronger authentication method if the user, for example an employee, tries to log in to the company's systems outside of the standard working hours. The possibilities here are countless. Once the user is authenticated and claims are asserted about them, it's time for the token service to issue secure tokens. It's important to keep these components separate, the authentication service and token service. As you've just seen, authentication is a very complex process, and the authentication service should not have the additional burden of being responsible for issuing tokens. Issuing tokens based on the authorization service's assertions can also be a complicated process itself. The token service must be sure that it can issue the types of tokens the client requested. For example, can the client get a refresh token? And if so, how long should the refresh token be valid for? Or should the access token be a JOT or an opaque token, etc.? Another important role of the token service is to map the assertions made by the authorization server to claims that end up in the tokens. It should know which claims can the client have access to based on the requested and consented scopes, which claims should end up in an ID token and which in an access token, etc. Popular standards used by a token service are Auth2.0 and OpenID Connect, which regulate the process of issuing tokens, and the JOT specification, JSON Web Token, a standard for issuing web-friendly tokens with strong integrity and security in mind. Token service's role can sometimes be assumed by a federation service, an external service which uses standards like SAML or WS Federation to issue secure tokens. To sum up the identity management system, its four important components are the profile service and the identity store, which serves as a persistent store for the profile service, the authentication service, which has the utterly important role of authenticating the user based on the data from the profile service, and which issues assertions about the user, and the token service, which uses those assertions to issue secure tokens which provide either access to your APIs or data about the authorized user. The second pillar of the neo-security architecture is the API management system. It can consist of many small components and services, but there are two which will always be part of this component: the API gateway and the API management platform. Although at first, the API gateway may just seem like a reverse proxy, a server which forwards requests to a concrete API service, it is much more than that. The gateway is one of the levels of security for your APIs and provides a coarse-grained validation of the incoming requests. At minimum, it validates the path and method of the request and should also validate whether the request contains a valid access token. It can even perform some more sophisticated validation, like verify whether the access token contains scopes required by the concrete API. Let's have a look at an example. A client sends a request to get a list of the user's friends. It wants to get the list in JSON format and presents an access token. Before the request is passed to an API, which can actually return the list of friends, the API gateway performs initial validation of the request. It can check whether there is an API which listens on the friends path and whether the get method is allowed for the friends path, and whether the API is capable of producing a JSON representation of the resource. It can then check if there's a bearer access token in the authorization header, and if so, does it conform to the format used by the API? The gateway can check whether the token is valid. If it's a JOT, the signature can be verified and the claims checked. If it's an opaque token, the gateway can ask the authorization server whether the token is valid, and if it has access to the token's scopes, check whether it has the scope required by the API, for example, the friends read scope. Requests which fail this validation can be rejected by the gateway and will never make its way to the API. Apart from increasing security of your system, this also takes some load off of the APIs and the internal network. It also allows the APIs to focus on business-related validations and tasks. The gateway is a good place to implement centralized features, so that the APIs don't have to implement them on their own. Things like rate limiting or gathering some traffic metrics are ideal examples of features your API gateway can have. Phantom or split token flows are examples of security-related features performed by the gateway. They will be described in detail in the second part of this course. As noted before, separation of concern is one of the principles of the neo-security architecture. You should remember about it especially when thinking about the API gateway. The gateway is a part of the whole platform, which feels like a natural place to implement many different functionalities used by the APIs. But it is very easy to overload the gateway with features, and you should strive to avoid adding too many business-related features to the gateway. Once you have too much proprietary code and solutions in your gateway, it will be very hard to exchange the product for a different one, should such a need arise. You might get stuck with a subpar product because it will be too difficult or too expensive to move all the logic into a new one. An API management platform is another vital part of the API management service. The platform helps you manage your API definitions and configurations. It feeds the API gateway with the configuration needed for the validation of requests. Some API management platforms allow to perform the management through a portal that can be used directly by your developers who create the APIs. This gives you a central place where configurations can be easily managed and governance mechanisms can be applied. Let's have a look at the third pillar of neo-security architecture, the entitlement management system. To better understand the role of the EMS and the rationale behind it, first have a look at the simplified security flow in our platform. First, the client interacts with the token service, or in fact the whole IMS, to get an access token. It then uses the access token in a request, which is verified by the API gateway, and then forwarded to the API itself, so it can be processed and produce a response. In this flow, we can observe 3 levels of applying authorization policies. The first level is at the entry point to the token service. The second one is a coarse-grained validation performed by the API gateway, followed by a fine-grained validation which happens in the API itself. So 3 levels of authorization applied in different parts of the system: the token service, the API gateway with coarse-grained validation, and the API service with fine-grained validation. At each of those points, different authorization policies are applied. For example, at the entry point to the token service, the policy tries to answer questions like, is the client known? Is it allowed to request the scopes it is asking for? Can the client receive those types of tokens? Or can it request tokens for this concrete audience, etc.? At the API gateway level, the coarse-grained authorization policies are applied. We already mentioned them before. The API gateway checks whether the access token is valid and is there an API corresponding to the request path, method, content type, etc. The gateway can have some other policies like checking the allowed rate limits for the client or whether the client is active or not, and others. Finally, at the API level, the fine-grained policies are applied, which can answer whether the request can be processed in a business-related manner. The API should check whether the token it received is valid and has all the properties it expects. For example, does it come from a trusted issuer? Is it issued for the right audience? Is it the right type of the token, etc.? Then the API should perform detailed business validations, like, is the user the owner of this resource? Do they have privileges to read or write that resource? If it is a payment operation, then it can check whether the user has enough balance to make the operation, etc. When your system grows and there are more and more such authorization policies to be applied, it becomes a burden to keep track of all of them and to properly manage them. The policies are defined in different parts of your system, which requires advanced tracking and bookkeeping. This is where the entitlement management system comes in handy. The system abstracts all of your authorization policies to a centralized system, where they can be managed through a policy administration point. The parts of your system mentioned before become the policy enforcement points, where policies are used to either allow or deny access. Whenever an authentication decision needs to be made, a policy enforcement point queries the policy decision point, which uses the information provided from the request and any policies definitions kept in the policy information point to provide the policy enforcement point back with a decision whether the request should be authorized or not. Although this system may seem overly complicated for smaller solutions, in bigger organizations it becomes a valuable asset. It helps to comprehend and manage all of the policies applied in different parts of the system. A good example of an open standard in the field of entitlement management systems is the Open Policy Agent engine. That's the end of the first part of this course. If you have any questions or comments, please let us know using one of those contact options. Thanks for watching.